Okay. Now, like in the other chapters, we start out with a type of equilibrium problem that's a little different than the usual ones that we'll be doing for the majority of the rest of the chapter. Here we get into one that's much more like the normal ones. I shouldn't say the other ones are abnormal, but we only see one of that type. So here we are, we have our KSP expression, and we have our initial, our change, our equilibrium. We have 0 of the ion. Then there's a minus here, but since it's solid, we don't concern ourselves with it. Plus 2x, x, and 2x. Oops. And then we have our KSP expression, which is lead and chlorine, or chloride squared. So we have x and 2x squared, and this becomes 4x to the third. And we should get used to seeing that. Anytime we have a 1 to 2 ratio here of unknowns, we'll end up with 4x cubed. Now, the KSP for this problem is listed, and that's what we normally have. The previous one we found KSP, like we found KC in the chapter 14 and KA in chapter 16. All right, come on. All right, down you go. Sorry, kitty cat's in the way. Now, our table then will give us KSP is equal to lead chloride 1.60 times 10 to the minus 5. So 4x, and this will give us the will give us x. If we solve for it, we end up with 0.0159 molar, which is the concentration of the lead chloride in solution. But the lead chloride breaks up into ions, so we can take, so that's where we get these concentrations, but that's actually not what they're asking for. They want just the solubility of lead chloride. So anytime you find X, you found the molar solubility. If they want to know the concentration of chloride, you just take X times 2. The concentration of lead would be the same as the concentration of the lead chloride. So that X will always give you molar solubility. That's the key thing. Even if this was a 3 and this was a 5 up here, X is the molar solubility, because that's the concentration of the compound intact before. So you can picture it as being a solid and goes into aqueous solution and then it breaks up. So thinking of the compound as being intact in the solution, that would be the concentration, and that's the molar solubility. But they also want the solubility. If they just say solubility, they generally mean in grams per liter. So we take 278 grams, which is the molar mass of the lead chloride. So that's for lead chloride, and we get 4.42 grams per liter. So every liter of solution will contain 4.42 grams of lead 2 chloride. All right, then here's one that's a little trickier. We have lead 2 arsenate. That breaks up into 3 lead and 2 arsenate ions. So the ice table, this is 0. This is plus 3x plus 2x. And we put that into the KSP expression. This is lead 2 cubed. And then the arsenate. And so this is 3x cubed, 2x squared. And this is comes up to be 108 x to the 5th. So when the ratios are 3 to 2 and we just have x's involved, you should expect to see that number. So there's certain numbers that we have for these different ratios that will become very familiar. I'm not saying that you need to know them now. You'll just learn them as you go. They should become very, let's see, should be ones that, oh, was I looking at the wrong one? Lead arsenate. And it should just become very familiar. So we have 10 to the minus 36. So Then we solve for x. So it'll be 4 times 10 to the minus 36 divided by 105 to the 0.2 power. That's going to be the concentration. X is the molar solubility, so it's going to be the concentration of this stuff as if it were intact in solution. It's not. But if it were intact, this would be its concentration. And I'm going to, let me redo that just to check. Yeah, I thought there might be something a little wrong about that. Yeah, so this is not the answer. So that would be 3.28 times 10 to the 8th molar. It seemed way too small to be something that because we'd have to take that number, x, take it to the 5th power, and then multiply it by 105, and that should get us back to this number, which it does, 3.99. Yep. So that is the molar solubility. And then if we want the solubility, that's going to be in grams per mole. So we take the molar mass of our compound, which I determined to be 899 grams per mole. And I checked that 3 times. I know it's got to be gigantic, but it just threw me off when I was looking at it. And so I just don't trust it, even though I did it 3 times. So that's 2.95 times 10 to the minus 5 grams per liter of the solution. So you'll work it out, get everything in terms of x, solve for x, and that will give you the molar solubility, because that x is going to be the concentration of the whole intact thing. Then it breaks up into ions. It's 3 lead and 2 arsenate ions. And again, if they wanted you to tell how the concentration of lead ion, you just take x, multiply by 3. If they want arsenate ion, multiply by 2. And that is the deal.